Hello, and welcome to the fourth part of this GNU radio tutorial series. Here we're going to have a look at using a random source to output a byte stream. We're going to put that into a modulator, add some Gaussian noise, and then analyze the resulting signals using these graphical sinks. Previously, I'd used the Gaussian linear feedback shift register to generate a pseudo-random sequence. Remember, this outputs a byte stream where only one bit is valid in each byte. And the unpack-to-pack block would take 8 of these bytes, and therefore 8 bits in total, and pack them into a byte where all 8 bits would be valid. Here though, we're going to use a random source to have more control over the generated sequence. We're going to output a byte stream, and the minimum and maximum values have been set so that the output values will occupy the complete range afforded by 8 bits. Remember that the maximum value should be 1 greater than the maximum that you want to appear in your stream. Here the sequence will be 100 bytes long and will repeat forever. Before we have a look at the modulators, let's have a look at the signal flow as it travels up here into the throttle block. It then goes into the UChar to float block. Remember, we have a byte stream, so the UChar to float will take the incoming unsigned bytes and convert them to their floating point representation. There's also the char to float, which would treat the incoming byte stream as a signed byte. But here we want the output floating point representation to vary between 0 and 255. Therefore, we can analyze the output of the random source using the scope sync and the histogram sync. We have two modulators here. One is a QAM modulator and the other one is a DPSK, or differential phase shift keying modulator. Let's have a look at that one first. We have some properties here to set how the information bits will be modulated onto a complex baseband signal. Let's do a very quick recap. Phase shift keying works by changing the phase of a carrier wave to convey information. The simplest form is binary phase shift keying, where you have two possible phases of your carrier. We've got the original at 0 degrees and the flipped one at 180 degrees. And you can deconstruct how phase shift keying works by plotting the symbols that will be transmitted on a constellation diagram. Remember, the constellation diagram is just a complex plane, so you've got the real and imaginary axes, and each symbol will therefore show a particular phase. So the symbol that will convey the bit 1, let's say, will be at phase 0, and 180 degrees from that will be the second symbol conveying the bit 0. So each time we have a bit coming in, it will look up the appropriate symbol on this constellation, extract the phase from that, and then modify the carrier using that particular phase that's looked up. This is just binary, so we have two symbols. We can go further and increase the number of symbols to 4. Therefore, each symbol will actually convey 2 bits. The easy way to figure this out is simply 2 to the power of n, where n is the number of bits, and that gives you the number of symbols on your constellation diagram. QPSK, otherwise known as quaternary or quadrature phase shift keying, is this particular form here, and you'll also notice that if we look between successive points on the constellation diagram, you can see that the individual bits only ever vary by 1, and this is known as grey coding, which means that if you were to take a symbol and it would accidentally be misclassified as an adjacent symbol, you would only get 1 bit wrong, whereas if you just simply counted up in binary going around the circle, then you would get instances where both bits would be wrong. Let's say you had 0, 0 and 1, 1, or 0 and 3 side by side, and you misclassified, then you would get 2 bits wrong. So grey coding is very handy. We can even go further. There are different fancier forms of phase shift keying, such as those that cause the complex signal not to pass through the origin, but I encourage you to read more about that separately. Here we have 8 PSK, where we have 8 points on our constellation diagram, 8 symbols, each encoding 3 bits. And you can set all of that in GRC using the type. So here we have BPSK, QPSK, and 8 PSK. And this will determine how many bits through each iteration it will consume from our incoming byte stream, because this selects the order of the modulation. Now the D is also important, and that relates to this property here, the differential encoding, because with phase shift keying, it's important, if you don't have differential encoding, to ensure that the demodulator is correctly synchronized to the modulator. That is, its carrier wave is using the same reference, so that, for instance, when you're talking about the phase shift of 0, then they're referring to the same synchronized wave. This is often not possible because the transmitter and receiver are separated, and therefore you can use differential coding. What this means is that for each bit coming in from your bit stream, it will take the bit that you intend to transmit. You can binary add or XOR that with the last bit that was actually output from the differential encoder, and that resulting bit will be the one you send. That's shown here in this block diagram. So you have them coming in, the previous result is stored in memory, and then you XOR that or add that to produce the next bit to actually transmit. And this is very helpful because on the receive side, the bit that you actually get back out of the demodulator depends upon the bit that was received from the phase shift keying demodulator and the previous one that it output, and that's shown here in this block diagram. So you have the bits coming directly out of the demodulator, going into some memory. This stores it, the previous one, it takes the current one and adds that to the previous one, or XORs that, and then you get your resulting bit. And what this simply means, in summary, is that this will look at changes in the bit stream as opposed to the raw bit values themselves. So for example, if your previous 2 bits coming out of the demodulator were 0, or both 1, so they haven't changed, then you would output a 0. If they had changed, so the current bit is 1 and the previous bit is 0, or vice versa, then you would output a 1. So this looks for changes in the stream rather than at the individual bits. And that means that if your demodulator and modulator are not synchronized, so they don't have the same reference, then that doesn't matter. This takes care of it. But if they didn't use this particular system and they weren't synchronized, then you would end up inverting your entire binary stream, and then you'd be scratching your head as to what's going on. There's another way of getting around that, not using differential coding, which is called looking for a sync word, and that's used in certain schemes like digital video broadcasting for satellites. But again, that's another way of doing this. This has one particular drawback regarding bit error rates, but I encourage you to read about that here. Let's go back to the properties now. So you can turn differential encoding on and off here. Gray coding we mentioned before, you can actually turn it on and off as well. The samples per symbol is how many complex baseband samples will be output per incoming symbol. This is the interpolation factor that the resampler applies to the internal pulse shaping filter. Now we've set that to a variable here, we've set that to 8. Verbose prints out particular information about the filter when you run the flow graph. And logging will actually create additional files that contain the complex baseband stream sampled from particular points through the modulation process. The excess bandwidth here is related to the internal pulse shaping filter, which is a raised root cosine. And I encourage you to read more about this. Here's a good article. There are several other articles that I've linked to below. And the excess bandwidth parameter actually controls what's known as the roll-off factor, or beta here, and you can see the frequency response and the impulse response graph for different values of B, and this controls the amount of excess bandwidth that will appear in your complex baseband signal. That's often a very important parameter control when you need to constrain the bandwidth of your signal within certain limits. So let's move forward now. We have a phase shift keyed complex baseband signal coming out, and we add it to a Gaussian noise source. We can vary this at runtime using the variable slider. The output of that goes into the throttle. Now notice that the position of the throttle is actually after everything that's occurred before. So we've gone from bytes to bits, taken a certain number of bits at a time to generate symbols, and for each symbol we generate a certain number of complex baseband values, and here we're going to throttle that. So we're saying that we're going to throttle at 100,000 samples per second of complex modulated baseband. We distribute that amongst these graphical sinks. Now we have the usual suspects like fast Fourier transform, waterfall, and scope, but I'm going to concentrate here on the Constellation sync and the fast autocorrelation sync. I'm going to launch the flow graph in a moment, but just before I do, bear in mind that because we're using phase shift keying, the Constellation sync is perfect for plotting the resultant symbols on a complex plane just to see how that signal looks. Now the parameters here have been tuned to the phase shift keying, so M is set to 4 because we're using QPSK, and the symbol rate we have calculated using this expression, so the sample rate that we're using, which is in this variable up here, divided by the samples per symbol that we've set in this variable. So this will perfectly lock on to our signal. And then the constellation size is the number of points that you actually plot per update of this graphical sync. So I've decreased that a little bit so it updates more often. The fast autocorrelation sync, as I mentioned previously, is used to find periodic components in a signal. And I'll delve into the size value in a moment, but essentially this will control the length of time over which it will try and find periodic components. Also, just bear in mind that we have the sample rate set in all of these sinks, but the sample rate does not control the rate at which these sinks will actually consume data or take it in. They will just take it in as it comes. It simply controls quite often how the axes are labeled so that it can calculate the time span over which it's actually processing data and give you the correct range on those axes. So let's launch this now. Here we have our complex baseband output from the modulator, and as you can see, if we look further down in amplitude, we can see several orders of magnitude down it continues on. That's because we have no noise set there at the moment. The fast autocorrelation sync is showing us these peaks, which is good. We expect them because we have a repeating random sequence. We often look at the first major peak, and that reveals to us the shortest repeating component within our signal. So we'll come back to that in a minute. Let's also look at the random sources output. So if we zoom out a little bit, we can see those 100 samples repeating over and over again. And the histogram sync, this is interesting because it looks like it's frozen, but in actual fact, bear in mind that because our sequence is of length 100 and our frame size is 1000, it's actually plotting the same 100 over and over again 10 times. If we were to decrease this to say 50, which is less than 100, then it springs to life. So just bear that in mind if you're wondering why it's frozen. The scope will show the complex baseband stream. So this is what a PSK signal looks like. It's got the real and imaginary components fluctuating, and at any one point you can sample the phase, and if you sample it at the right point, that will give you the symbol and therefore the bits that you've encoded at that sampling point. The waterfall reveals our signal over time, and as you can see, it's occupying this particular bandwidth here. The Constellation plot therefore shows our symbols, and remember we're using QPSK, so we expect to see these 4 symbols or 4 points grouping of points on our constellation plot, on our complex plane. And because we have no noise, there's very good separation between these symbols. So it's very, very easy to classify a symbol in terms of the bits that it actually encodes. If we have a look at the Gaussian noise source now, remember that it's off, so we won't see anything here. But let's increase the noise level now. And immediately we see a change here. So we see on the FFT plot we have this broadband noise, and on the histogram we actually see this Gaussian profile. And in proper scientific simulations, this is commonly referred to as additive white Gaussian noise, and the constraint is that it's wideband noise with constant spectral density and a Gaussian distribution of amplitude. And that's what we're seeing here. There's a little bit of a twist to it in terms of the fact that we're generating a complex floating point noise source. Internally at the moment, GNU Radio has a separate Gaussian noise source for the real and complex parts, but that still results in this good uniform distribution here on the FFT of the spectral density. Now, we've increased the noise, so if we look back at the FFT, we can see that previously it was containing no noise, but now we have a noise floor that's come up. We still have these peaks on the fast autocorrelation. With the scope, we can see that there's been a lot of noise superimposed on our original modulated output. And if we look at the waterfall, that's also changed as well. You can see the noise floor has come up. And this is a good time to auto-scale again. And on the constellation plot, we see that our symbols have started to spread out now. So they're no longer as tightly packed as they were. There's less of a separation, and this is what you will commonly see when you sample signals in the wild, because they will inherently contain some noise. If we change the noise, you can see that they come back together, and the more you increase it, the less separation there is. And once again, this is an example of where forward error correction is important, because symbols will inevitably stray into the territory of other ones and then be misclassified, so you'll output incorrect bits. But if you have forward error correction, you can hopefully, at the very least, detect and hopefully correct those errors. So let's take it back down again, so we have some good separation. Another thing you can do here is, if you look at the line link mode, you can see, let's just turn the noise further down so there's better separation. You can see how you have the lines ending up at our 4 points on the constellation, but then every time there's a change of phase, you get a line that jumps from one point to another, and you can see the phase changing, jumping from one symbol to the next, often across the origin as well. Now if we look at the scope, before I go to the scope, just keep in mind that the constellation plot internally is synchronized to this PSK symbol because we've given it the correct parameters, and therefore it will sample the phase at the appropriate time. So you get these very clean lines and the clean points coming up. Let's look at the scope now. Remember the scope, there's no synchronization at all, so it's just going to draw all of the complex baseband symbols coming in. So if we switch to XY mode here, we see the dense regions in the corners that represent the symbols that we want, but we also see all of the transitioning samples as the baseband stream transitions from exactly one symbol to the next. And if we start increasing the noise, you can see that fluctuate even further. But if we go to line link here, then you can see these areas of transition, and that's what's generating these curved lines. So it's actually plotting, if we stop that for a moment, it's actually plotting all of the complex baseband symbols from when they are at a particular sampling point as they transition through the origin or across to another symbol on the constellation plot. So you can actually get a sense here of what the noise is like and how well the modulation is working with the channel that you're sending it through. Now let's look back at our fast autocorrelation. Let's increase the noise again. Back to these peaks that I was telling you about. The way to actually interpret the length of the periodic component is just simply by looking down at this axis. And just wanted to make a point about how this is actually drawn. Remember, I was telling you that we have the sample rates here. The size value of the autocorrelation will relate to how long or the period of time over which the autocorrelation is graphed here. And the way you can easily figure that out is by taking the size value that you've placed in there. I have an expression, but that's evaluated to 32K. You divide that by the sampling rate, which is 100,000, and then you divide it by 2. Internally, an autocorrelation uses a neat trick, which is that the autocorrelation is equivalent to the inverse Fourier transform of the power spectrum. And I encourage you to read a bit more about that because there's some fascinating stuff you can do with Fourier transforms. In summary, the power spectrum is the squared modulus of the Fourier transform of the original signal. This will yield a real valued vector with no phase information. The autocorrelation can then be found by taking the inverse transform of the last result. The fast autocorrelation sink, though, simply takes the forward transform. Remember, because we took a transform of a real valued vector, we're going to have a spectrum that is symmetric about the middle frequency, and therefore we can ignore the top half. And that's why you need to divide it by 2. So if you do 32K divided by 100,000 divided by 2, you will end up getting the length of time in seconds over which you will actually do the autocorrelation. And if you were to divide that out, you will just get it a little over 160 milliseconds. So that's how you can determine the length. The other important thing to note is that when you do that, often start with greater length and then start decreasing, because due to the nature of the operations and the lack of filtering, you'll end up having often a wraparound. If you look at the peaks here, this is the first major one, and then you always get the multiples, so it'll slowly decrease in amplitude. But then immediately, if we start going back again, it's wrapped around, so you get the peaks that would continue off to the right, but because the fast autocorrelation length is too short, it wraps around and then starts coming back again. So don't be confused by these peaks. If they look like they're wrapping around, then you need to increase the length of the analysis here. Now, let me demonstrate why, in fact, fast autocorrelation is such a powerful tool. We can take the noise all the way up to 1, but we still have some semblance of our modulated PSK stream here. Let's now bump the noise right up. You can see the original signal that we're modulating has been completely submerged under this higher noise floor. And if we look, for instance, at the scope, it looks like a complete mess. The Constellation will have no lock whatsoever. And if we look at the scope in line mode, it just looks like noise. I'm going to enable averaging now on the fast autocorrelation sync, and let's wait a moment to see if it will reveal any useful information. While this happens, remember that there are a lot of very weak signals that are invisible to the naked eye on an FFT plot, as they're present below the noise floor, yet they still contain information that can be decoded. An example of this is the signal broadcast by satellites in the GPS constellation. By the time these signals arrive at the Earth, they're extremely weak. GPS data is modulated using CDMA, or a technique that uses code division to allow multiple data streams to be modulated onto the same shared frequency. The original data is made to occupy a larger bandwidth, which is why CDMA is known as spread spectrum modulation. And a spreading function, usually an orthogonal pseudo-random stream, is used to distribute the signal's energy over a larger bandwidth than would otherwise be occupied by an equivalent narrowband signal. We could use the autocorrelation to find the existence of the coarse acquisition signal on the L1 frequency by looking for a peak at 1 milliseconds. Let's have a look though at the autocorrelation here. You can see that the noise has been averaged into a thin line. Remember that this is due to the perfect artificial simulation of a noisy channel. However, you can see appearing just above the thin line these peaks, which although small, they're still discernible and ostensibly line up with the large peaks that we saw earlier on. This is quite remarkable because when you consider the original signal is well below the noise floor, you can't see it at all on an FFT plot or the waterfall. So let's investigate that first peak again. It appears to be placed just after 30 milliseconds. So let's confirm whether this is correct by doing a little bit of arithmetic. Just to recap, before we had 32k divided by 100,000 divided by 2, and if we multiply that by 1,000 to get milliseconds, you can see we get 163.84 milliseconds, and that's the duration of the autocorrelation. Now let's look at how we arrived at that peak. Remember, we've simulated a random source, we know the length of it, so we have 100 bytes repeating over and over again. We multiply that by 8 to get the number of bits repeating over and over again, and because we're using QPSK, that's going to take in 2 bits at a time, which means that we're going to have 400 repeating symbols on that complex constellation diagram. Now, the samples per symbol we've set to 8, so for each symbol it's going to generate 8 baseband samples, so we multiply that by 8, and therefore we get 3,200 repeating complex baseband samples coming out of the PSK modulator. That's the length of the stream that's going to repeat over and over again. We've added some noise to that, but if this is our length of the stream, we need to calculate in time how long that will actually last, and we know that we're using a sample rate of 100,000, which has been input into the fast autocorrelation block. So if we divide that by 100,000, and then that's in seconds, so we multiply by 1,000 to get milliseconds, 32 milliseconds, and if we look, that is pretty much where that initial peak lies. So that pretty much demonstrates the power of the autocorrelation sync. Let's do one more quick demo. If we use QAM, we can see what QAM will look like. For reference, this is what a QAM constellation looks like. It uses both phase and amplitude to encode these symbols. This is 16 QAM, so we have 16 points on the constellation, and each symbol will encode 4 bits. Funnily enough, the constellation sync in a situation of no noise will plot this correctly as well. So here we have QAM 16, and if we run this, we have different peaks here because it's actually taking in 4 bits at a time instead of 2. But on the constellation sync, here we have our 16 points appearing. As soon as I introduce a little bit of noise though, it should fall apart pretty quickly. The constellation sync is really only designed to handle much lower orders of phase shift keying only. And we can see what it looks like on the scope as well. Looks a little bit more complicated than phase shift keying because we can see these additional changes in amplitude encoding that additional information. On the waterfall, it looks similar. One thing I wanted to point out before though is even on the waterfall, because we have this repeating sequence with 0 noise, you can actually see the repeating blocks of pixels essentially on the waterfall as the sequence repeats. So you can see in the center there's this sort of bright dot, and that repeats every so often as we go down. And that brings us to the end of this demonstration. Thanks for watching, and see you in part 5.